So you remember exponential function has a form a to x. A to x. And we assume that a is a base here. So a is positive. Okay? And usually we assume that a is not equal to 1 because 1 to any power is 1. So two particular exponential functions. If you recall two particular ones, for examples, we have two particular ones. The first one, exponential growth. That is f of x equals a to x. And we have exponential growth when a is bigger than 1. So when base is bigger than 1. And the graph of it is going to look something like this. So it's going to exponential growing. And intersection here, a to any power, a to the 0 is 1. So, okay. So that's exponential growth. So it's increasing rapidly. Okay. And the second one is exponential decay. That is, again, our exponential function. And here we assume that we have small base a less than 0. I mean, a less than 1, bigger than still positive. And exponential decay looks something like all in. So we try to approach 0 when x is approaching infinity. Okay? And it's decreasing. And again, a to the 0 is 1. So that's okay. So what we want to do is we want to find derivatives of exponential functions. So the first question is, what will be the derivative of a to x? Okay, so that's our first question. So that's the one which we'll try to address. So let me try to answer on this question. So to answer this question, I have to recall what is the limit definition of a derivative. So I'll start working on that. So using the limit definition of a derivative, we have derivative of a to x equals limit when h is approaching 0, f of x plus h minus f of x over h. So in our case, because we have function a to x plus a to x, so we have a to x plus h minus a to x divided by h. So we're going to get limit as h approaching 0, h. Our property of exponents, you recall if you have sum in exponents that corresponds to product, a to x times a to h minus a to x. So we have limit as h approaching 0, so we can factor a to x out. We're going to get a to h minus 1 divided by h. So we're going to get a to x has nothing with h, so we can take it outside of the limit. Right, so we get that. Interesting looking expression. So let me rewrite it one more time. So we'll write that where we started. So that's where we started. That's where we ended. So I'll write them together. So we got derivative of a to x equals a to x times limit h approaching 0, a to h minus 1 h. So that's what we got for the derivative of exponential function. Okay. And now we can plug in different, so we can plug in different A. We can calculate different derivatives. For example, we can calculate what will be derivative of 2 to x. Will be 2 to x limit 2 to h minus 1 over h. Derivative, for example, of 3 to x is going to be 3 to x limit 3 to h minus 1 over h. Okay. And now to approximate here, h is approaching 0, h is approaching 0. So now to approximate each limit, say you choose h close to 0, say 0.1, 0.01, negative 0.01, and you approximate the limit, okay? And then you get you some approximation to that number. So by picking h, say 0.1, 0.01, negative 0.01, and so on, you will be able to evaluate that limit. You will do the same here. Okay. So what it turns out, if you do that, then derivative of 2 to x, so if you do that, then derivative of 2 to x is going to be 2 to x, and here number will be slightly less than 1. Okay. If you multiply, if you take derivative of 3 to x, you're going to get 3 to x, and you do the thing when you substitute in small a values of h for that limit, you'll get number slightly bigger than 1, right? For 2 to x, we get 2 to x times derivative of 2 to x is 2 to x times something smaller than 1. For 3 to x, we're going to get 3 to x times something slightly bigger than 1. So to be exact, derivative of 2 to x is approximately 0.69 times 2 to x. And derivative of 3 to x is approximately 1.10 times 3 to x. Okay, so that's what we got. And then you can play a little bit more with these numbers. So you can take, for example, instead of choosing 2 and 3, you can choose 2.5, 2.75. And if you do that, then you realize that somewhere between 2 and 3, there is a number so that its derivative will be that expression a to x, and that coefficient in front is going to be exactly 1, right? Somewhere between 2 and 3, there should be a number where that coefficient will be exactly 1. For 2 to x is slightly less, for 3 to x is slightly more, so somewhere in between it will be exactly 1. So that number is going to be called e. Okay? So derivative of e to x equals to e to x. So somewhere between 2 and 3, there is such a number, and that number is going to be called e. And it has a property that its derivative e to x times 1. And that number, you can find it on the calculator if you like. So where e equals 2.71828. Okay. For example, let's find few derivatives. Find the derivatives. E to the 2x. So we're going to treat exponent as our inside function. So inside function u equals to 2x, outside e to the u. So derivatives of inside function is 2, derivative outside e to u is e to u. So final answer is going to be 2 times e to the 2x. So that's the chain rule. Because derivative e to x is e to x. For example, derivative e to 1 plus x squared is going to be equal. So go ahead, give it a try. Same thing as we just did. Exponent is going to be our inside function, so we're going to take 2x e to 1 plus x. For example, we can have, say, x squared times e to the negative x. We can take its derivative. Product rule, write down your scheme for product rule. Fill up. Derivative x squared is straightforward, it's 2x e to the negative x plus x squared. Derivative e to the negative x, inside function is negative x, so derivative inside is negative 1 e to the negative x. Okay. So we can get 2x e to the negative x minus x squared e to the negative x. If you like, factor out common x times e to the negative x out. I'm not sure if it's going to look a little bit better or not. So I don't know. Okay, so now we know how to take the derivatives of exponential function e to x. Okay,